So next, let's go on to determine extreme values. So we'll use this extreme value theorem. So again, what is it? The extreme value theorem says if f is a continuous function, if it's defined over a closed and bounded interval, some I between a and b, where a and b are included, so that's closed, and is bounded because a and b are finite, don't run off to infinity anywhere, then we are sure that there exists some point at which this f attains its minimum, and some other point in this interval, might be on the boundary, might be somewhere interior, where this f has a maximum. So that's what the extreme value theorem tells us. So we know for sure there is a maximum and there is a minimum. So how can we use this? Well, if we are sure that there is a minimum and a maximum, well, we are sure as long as f is a continuous function. Well, if f is a differentiable function, then it's also going to be continuous. And the interval is, in this case, closed because a and b, the endpoints, are included, and bounded because they are not infinite. We know for sure that we can apply the extreme value theorem, so we know there is a maximum and a minimum. What remains to do is, well, we need to figure out what are the candidate points. So part of the candidate points for this maximum and minimum were the stationary points, right? So we have to figure out when is the derivative going to be 0, because that's the definition of a stationary point. So in order to do that, we first have to find out what the derivative is, to factor that. The other candidate points are the endpoints of this interval, so a and b. So we know what, and once we have done that, what the candidate points are for the maximum and minima of this function f. We also know by the EVT there must be a maximum and there must be a minimum. So what remains to do is, well, just figure out what are the function values for each of the candidates that we have found, and the one which is highest must be the maximum, the one which is lowest must be the minimum, and that will actually be the endpoint for this analysis. So let's have a look at how that works. So we want to, in this example, figure out what are the extreme values, so the maximum and the minimum, of this particular function, f of x. So what the function is 2x squared divided by x to the 4th plus 1. So this function is a nice and differentiable function. So it's a quotient of two functions, but actually the denominator is never going to be 0. So no problems there either. So it's a nice combination of various differentiable functions without any problems if you wish. So this is going to be a continuous function. And it's defined on an interval x between -2 and 2. And see, that's a closed interval, -2 and 2 are included, and of course it's bounded, right? It doesn't run away to infinity. So we have a function which satisfies all these requirements. It's continuous, it's defined on a closed and bounded interval, so we know there are a maximum and a minimum. So we just need to figure out what they are. So let's do that actually on paper. So on paper, let me rewrite this this function fx equals 2 times x squared divided by x to the 4th plus 1, and it's given on an interval df which is closed and bounded in between -2 and 2 with these endpoints included, so closed interval. So we need to figure out what are the candidate points for the maximum and the minimum. So it must have by the EVT a maximum and a minimum, so let's just figure out the candidates. First candidates are stationary points, or in other words, the point at which the derivative is going to equal 0. So what's the derivative? What is it actually? F prime x is, well, this is a quotient, right? So we need to use the quotient rule. So how do we use the quotient rule for taking a derivative? Well, we first take the derivative of the numerator, which is going to be 4x, and multiply that by the denominator, x to the 4th plus 1, and from that we subtract the numerator itself, 2x squared, times the derivative of the denominator, which is 4 times x to the power 3. And that result we divide by the denominator squared. Right? So this is just the quotient rule that we covered last time. And so let's simplify this function because we want to know when 0, right? So we want to factorize this function. Well, the denominator we leave as it is because it's never going to be 0. You can see this because x to the fourth is always a positive number, or plus 1, even more positive. It's going to be bigger than 1. Taking the square remains a positive number. So never going to be 0, no problem there. We won't have to touch it. So we leave that as it is, but the numerator we can write a bit differently. So let's get rid of those brackets. For the first term, this gives us 4 times x to the 5 plus 4x minus second term 8 times x to the power 5. So x squared times x cubed, that's x to the power 5 divided by x to the 4 plus 1 squared. First bit. Now I can simplify, of course, this numerator because we see here the 4x to the 5 minus 8 times x to the 5. So it's minus 4x to the 5 plus 4x divided by x to the 4 plus 1 squared. We're almost there because this thing we can easily factorize. So you see this minus 4x sitting in both terms, so we take that out. So minus 4x. Well, in order to get the first term, we still need to multiply by x to the 4, right? So this first bit gives the minus 4x to the 5. And to get the plus 4x here, we have minus 4x, you have to multiply them by minus 1, right? So this is a factorized, almost factorized form of the numerator, but we're not quite there because this factor over here, we can simplify that a bit further still. So we see this is actually minus 4x times, well, x to the 4th is actually a square, right? It's x to the power 2 squared. And 1 is also squared. So this is square minus a square. So this should ring a bell, and the bell is, well, we need to apply one of these special quadratic expressions. So we can rewrite this actually as x squared plus 1 times x squared minus 1 by this quadratic identity, divided by what we have in the denominator. This factor we leave alone is, again, it's always going to be positive, so we cannot reduce this any further. But this one, again, we can use the same quadratic identity because again it's the square minus 1 squared. So let's write this as minus 4x times x squared plus 1 times x plus 1 times x minus 1. X plus 1 times x minus 1 makes x squared minus 1. Okay. And now we are essentially done because this is how far we can go. And now we can actually read off from this. We asked for the stationary point, so f prime x equals 0. Well, just need to figure out when any of these factors in the numerator is going to be 0. So this one I already told you is never going to be 0. It's always going to be bigger than 1. Same way for the denominator. But each of these three factors can be 0. So the x equals 0 is the first stationary point. The second one is x plus 1 equals 0, or x equals minus 1. That's going to be stationary point, and likewise x equals 1 is going to be stationary point. So these are the stationary points. Stationary points. These are three of the candidate points for the maxima and minima for this function. What are all the candidate points? Well, it's not just stationary points, but we also need to include the endpoints. They're also candidates for the extremal points. So x equals minus 2 and x equals 2, the endpoints. So together, these 5 points will be the 5 candidates that we have for the maximum and the minimum of this function. We know there should be such a maximum and there should be a minimum by the extreme value theorem, as we discovered. So, well, which one is it? So which one is the maximum, which one is the minimum? Well, let's find out by just listing what f of x is at each of these points, and where it's highest in each of these for each of these 5 points, we'll find the highest and we'll find the lowest. So let's just make a table doing that. So x equals -2 is one of them, x equals -1 is one of our candidate points, x equals 0 is 1, and 2. So we need to know how high is f actually at each of these points. So how do we find that? Well, by plugging in those values in f itself. So this is f, 2x squared divided by x to the 4th plus 1. Notice, by the way, I didn't mention this before, but these 3 stationary points, they are actually in the domain, right? So all in between is -2 and 2, so that we can include each of these indeed. So let's compute the fx for each of these 5 points. So the easiest one is 0, I guess. So if I plug in 0 is 2 times 0 divided by 0 plus 1, that's just 0. Right? So the function value is 0 if I plug in x equals 0. So what happens if I plug in 1? 2 times 1 divided by 1 plus 1, that's 2 divided by 2 or 1. And same thing for -1. -1 squared is also 1. So here we get also 1. What happens if we plug in x equals 2? 2 times 2 squared, so 2 times 4, that's 8, divided by 2 to the power 4, that's 16, plus 1 is 17. So 8 divided by 17. 8 divided by 17. And likewise again, if we plug in -2, squaring this gets rid of the minus. So again, also here we find 8 divided by 17. So now we're there. There are 5 candidate points for the maximum and minimum. We figured out how high the function is, or what the function values at each of these candidates, and the only thing that we need to check is, well, which of these are the highest and which are the lowest. So clearly the 0 is the lowest value that we can attain, so 0 is going to be the minimum. So the minimum occurs at x equals 0. And the maximum actually occurs simultaneously at 2 points, namely x equals 1 and x equals -1, because the function value is 1, which is higher than 8/17. So 8/17 is approximately a half, and so 1 is bigger than that, of course. So x equals -1 and x equals 1 together are both the maximum of this function. f0 equals 0 and f-1 equals f1 equals 1. Minimum and maximum. So there we go. So let's get back to the slide then. So here's this computation of the derivative in order to figure out when is this derivative going to be 0, because that's the condition for the stationary points. So we factorize the derivative. We determined the candidate points x equals 0, x equals 1, and x equals -1. We had to add to candidate points not only the stationary points but also the 2 endpoints, -2 and 2. And then we listed the function values at each of these 5 candidate points. We just looked at this table, saw, well, the minimum is apparently taking place or occurring at x equals 0, where f equals 0, while the maximum occurs at x equals plus or -1, and the function value, the height of this function is 1 at that location. So this answers the question, and we can actually see in the graph that we did the right computation by verifying that the graph indeed also takes here its maximum at 1 and -1, equally high, and its minimum at 0. And these endpoints are actually neither maxima nor minima. Okay, so that's for this example. So sometimes we of course have a function or a case which does not satisfy the conditions of the extreme value theorem. So if we have again such a function that we are exploring, we would like to know, does this have a maximum or minimum? Well, we have to ask, if we want to apply this extreme value theorem, is this function continuous and is this interval I actually closed and bounded? And some of these conditions might sometimes not be satisfied. In that case, we cannot use the EVD. So in that case, f might not have a maximum or a minimum. And we saw examples of those already. What we can still do is check out the candidate points. So the candidate is still on the stationary point, the endpoints, if they are in the interval, and the points where f prime, the derivative, is not defined. So these kinks in the graph, if you wish. But now we can list them, but we cannot be sure without further exploration or further proof that there's either a maximum or a minimum at any of these candidate points. So for that we need some additional information. Sometimes we have some additional information that allows us to say, oh yeah, still, even though we cannot use the EVT, we still can say, well, this is the maximum or the minimum of this function. So we look at sign changes, we look at convex and concave functions, and we can also say a little bit about some limits perhaps. So let's have a look at what this sign change tool basically means. So if we know that a function has a stationary point, so here on the left hand side we see a stationary point at x equals c, and if furthermore we know, so the f prime equals 0, right, that's what the stationary point is at c. If we furthermore know that for each x smaller than that stationary point c, the function is increasing, or f prime is bigger than 0, it's upward sloping. While on the right hand side, so at c of course f prime equals 0, stationary point. And if we also know that on f for every value on this interval to the right hand side, the function is decreasing, or in other words, if you can be sure that f prime is smaller than 0 for all x bigger than c, well then that's sufficient proof to say, well, at this x equals c, this stationary point, there must be a maximum. So we see this, the sign of the derivative on this side is strictly, it's positive or 0 actually. The sign over here is 0, and the sign everywhere over here on the right hand side is negative. Well then, for sure, even though we are not, this might not be a closed interval, so it might be an open interval, so we don't have the EVT to rely on, but still we can conclude, well, this c must be the maximum of this function. And likewise, if we have here a function which attains a stationary point where on the left hand side the function is decreasing, so f prime is smaller than 0 everywhere for all x smaller than this hypothetical candidate point d, the function is decreasing, so negative derivative. Whereas on the right hand side, so for x bigger than d, this function is increasing, f prime is positive, then this d must be a minimum point. So here again we see a sign change of f prime of the derivative, in the sense that here f prime is negative, at d it becomes 0, and to the right of d f prime is positive. So f prime, the derivative, changes sign at d and at d only in this direction, then we are sure there's going to be a minimum at that point d. So that's one tool in our toolbox for even identifying extreme values for functions that do not verify all the conditions for the EVT. Another tool that we have is looking at convexity or concavity. So if you remember, a function is concave if its second derivative is negative. So this is an example of that. The second derivative of this function is negative everywhere on its domain. So then this function is a concave function. If we know the function is concave and it does have a stationary point, then the stationary point must be a maximum for this function. So here at this point c, the function will have a stationary point. The function is everywhere concave, so its second derivative is everywhere negative. Well, then we know for sure, well, this point c must be a maximum of this function. And likewise, if we have a function with an interior stationary point, but the function itself is convex everywhere, so f double prime, the second derivative, is always positive, then this d represents a minimum point. So let's try to work with this for an example. So this is a function which is a nice and continuous function, e to the power 3x minus 6 times e to the x. but it's defined on an interval, which is its whole natural domain, which is all the real numbers. So any value goes. So that's a nice enough interval, except it's not bounded, right? It's an unbounded interval, so we cannot apply the extreme value theorem. So we cannot know for sure that this function will have either a maximum or a minimum. So what can we do? Well, what we try to do is we can explore whether there are any candidates. In particular, there's no boundary points here, but there might be a stationary point. And if there are stationary points, we can try to figure out whether these two tools that I just discussed, whether they can help us in deciding whether that stationary point might be a max or a min for this function. So let's do that again on the paper. So there we go, we have the function f of x is e to the power 3x minus 6 times e to the x, and the domain of f, the interval on which it's defined, is the entire real number, so it's not bounded, so we cannot use the extreme value theorem. We can still find whether there are any candidate maximum points or minimum points, or stationary points in particular. So we're interested in the derivative of f. So what are those? Well, we can take the derivative of e to the power 3x by the chain rule. 3 comes down essentially. We multiply by the derivative of the exponential function, which is itself. And the second bit gives us again minus 6 times the derivative of the exponential, which is again the exponential itself. So this is the derivative of this function f, and we want to factorize it because we want to find the stationary point. We want to find out when it's 0. So in order to do that, I'm going to take out a common factor. The common factor that I would like to take out here is 3 times e to the x. So if I take out 3 times e to the x, what's left for this first term? Well, it's of course going to be e to the power 2x, right? So e to the x times e to the 2x. If I multiply these two powers, I have these two powers. I need to add up the two exponents, so x plus 2x makes 3x. So this first bit gives me the first term here. To get a second term, I just need to multiply by 2, so that's what's left here. 3 times e to the x times minus 2 gives you minus 6 times e to the x. So this is the factorized form of that same expression here. So now I'm interested in whether this function has a stationary point. Is there some x for which this actually f prime equals 0? Well, first bit here, first factor is never going to be 0, because e to the x is strictly positive. But the second one can actually be 0. So when is e to the 2x minus 2 equals 0? Can we solve that? Yeah, we can, because e to the power 2x equals 2 can be simplified by taking the logarithms on either side, or 2x equals the log of 2, or x equals a half times the log of 2. So for x equals a half log of 2, this factor is 0, therefore the f prime itself, the whole derivative, is going to be 0 at this particular point. So x equals a half log 2 is the stationary point for this function f. So this is a candidate point. There are no endpoints because this interval is unbounded. So the question is this candidate point, the stationary point, is this a maximum or a minimum perhaps, or neither of this function? So can we say something, we need either tool, so we need to look at convexity or concavity of this function, or look at sign changes of the derivative. So let's first ask, is this function, this f, is this perhaps convex or concave? Because that would help a lot. So what does that mean? It means, is the second derivative of this function, is it always positive or always negative? So let's compute the second derivative. F double prime of x, what is it? So I know what f prime, the first derivative, is, this one. So I need to take the derivative of that. So I can take the derivative of this one, where I would use the product rule to do that. I can also look at this unfactorized expression over here and take the derivative of that. And that's a bit easier, so let me do that. So the derivative of this first term, again this 3 is going down. Derivative of the second term remains 6 times e to the x. And let me factorize that again as 3 times e to the x times 3 times e to the 2x minus 2. So question, is this always positive, in which case this function would be convex, or is this always negative, in which case this function would always be concave? And the answer is going to be neither, because if you look at this, well, of course this first factor here, that's always positive, so that's nice. But this second factor here is actually ruining stuff, because if x is going to be very big, then e to the 2x is going to be a really big number, 3 times e to the 2x, even bigger. Minus 2 remains a large positive number. So sometimes this factor is positive, but sometimes this factor is actually negative, because if x is very small, a negative number, e to the minus 100, for instance, if x equals minus 50, 3 times e to the minus 100, that's almost 0, right? It's very small. If I subtract 2 from that, it gets well below 0. So sometimes this factor is negative, and sometimes it's positive. So in particular, it's not always of the same sign. Sometimes positive, sometimes negative. So the function f itself is not a convex function, and it's not a concave function either, because f double prime is sometimes positive, sometimes negative. So f is not convex or concave. So this tool in our toolbox doesn't help in deciding whether the stationary point here is a maximum or a minimum. But we had this other tool, perhaps you can use that. And this other tool was, well, does this f prime, the derivative, actually undergo a single sign change at a particular stationary point? So let's look at the sign diagram actually of this f prime. So f prime is the product of 3 times e to the x. And the second factor was e to the 2x minus 2. And there was one special value, which was x equals a half log 2, and this second term is actually going to be 0. The first term, I argue, is always going to be positive. Just draw a line wherever we are on the x-axis. This thing is going to be positive. The second term is going to be 0 at a special value. If x is smaller than that, well, e to the 2x is going to be smaller than 2. So with 2 subtracted, this whole thing is going to be smaller than 0. While on the right hand side is going to be bigger than 0. So f prime x, which is the product of these two, is likewise going to be negative on this side, 0 over here, positive on this side. So what happens to f prime is changing sign exactly once in the stationary point. Here f prime is negative, here of course it's 0, it's a stationary point, and on the right hand side it's always positive. So that means that if the derivative is always negative on this left hand side, this function is always decreasing on the left hand side. Of course, in 0, in the stationary point, the function is flat. The right hand side, the derivative is always positive, so this function is always going up. So what you can conclude, this function attains its minimum in this special point, in the stationary point, a half log x. So x equals a half log 2, this candidate, the stationary point, is actually the minimum of f. It was the only candidate, so we do not in particular have a maximum. So let's have a look again at the slide. So here we are on the slide. So we wanted to figure out what is the stationary point. So we determined what's the derivative of this function f prime. We figured out when it's 0, that gave us one answer, x equals a half log 2. We looked at all the candidate points, so for the stationary point, we do not have any endpoint because the interval on which we are working is the entire natural domain of all the real numbers for this particular function. F prime is always defined, so there are no kinks in particular in this function. So we need some further information because the EVT does not help us because we have an unbounded domain, find an unbounded interval. So the first tool that we looked at was, let's figure out what the second derivative is of this function. Perhaps that's going to help. We figure out what's the second derivative, but we also found that the second derivative is sometimes negative and sometimes positive. So in particular, this function is not convex and is not concave either. So we cannot use this tool, this rule, to draw any conclusions. But we fortunately had this other test, which was this sign change. So in order to check that, we looked again at this derivative of f, and we figured out, does this derivative actually have a single sign change? So we look at the sign diagram of that derivative, the red bit over here, by looking at the signs of the individual factors over here, and we figured out, oh yeah, indeed, f prime is negative on the left hand side of the stationary point. It's positive on the right hand side of this stationary point. So there's this unique sign change at the stationary point. And from this form, we see indeed that this candidate stationary point x equals a half log 2 is the minimum of f. There's no other candidates, so there's no maximum. So we will not guarantee there is a maximum. Indeed, there is none. So let's have a look at the graph, and this is the graph. You see indeed at this x equals a half log 2, this function attains its minimum, and at and this function never attains a maximum. It runs off all the way to infinity on the right hand side. So as a final example, let's look at an example in which actually convexity over concavity does help, and this is an example from microeconomics. So where we look at a firm which is producing some good. So it can produce any quantity Q, which at least any positive quantity, or can produce nothing. But of course, there's cost to production, and these costs are dependent on how much you're producing. There is some function C of Q. And we're going to assume here that costs are convex. So if you're going to produce more, it's going to be costing more, but in a convex way. So they're going to be marginal costs essentially are growing and growing. So in economic terms, you might say there are diseconomies of scale. So C double prime is bigger than 0, so costs are growing faster and faster as you increase quantities that you're producing. Well, if you produce something and sell it, it's not only cost that you incur, but you also get some revenues, of course, so from selling into the market. So suppose the market price is given, it's some parameter P, just value. So what are your profits from participating in this market? So profits pi as a function of the quantity Q that you're producing. Well, your revenues, of course, for each unit Q of product that you buy, that you sell in the market, you get P, the price. So your total revenues will be P times Q. But you're incurring costs from production, of course, which will be C of Q. Some function C of Q, of which you only know that's convex. So now if we check, actually profits are going to be a concave function in Q. So why is that? So concave means second derivative is going to be negative. Can we verify that? Well, what's the second derivative of this function pi of Q? Well, the first term here, if I take the first derivative of Q, I'm just left with a P, the number P. If I take a derivative of a fixed number, that gives me 0, right? So the second derivative of the first term gives me 0. Second derivative of the second term gives me minus the second derivative of C. So minus C double prime. Well, I know I was given that C double prime is positive because costs were convex. So minus C double prime is negative. So the second derivative of pi is indeed a negative quantity everywhere. So in other words, profits are always concave on this domain. So and we learned that if profits are concave and there is a stationary point, then the stationary point must be the maximum. So let's figure out, what does a stationary point mean? It means that the derivative is going to be 0. So what is the derivative? Well, derivative of P times Q, that's P. Derivative of this costing is minus C prime. So the stationary point is given by this equation, which we call the first order condition, right? The first order condition of optimization. P minus C prime equals 0, or P, this given price, the number, equals the derivative of costs. So now in economic terms, we know what it is, of course. The derivative of total cost, that's marginal cost. So what this says in economic terms, price equals marginal cost. So what we've just proven is that at the quantity which makes price equal to marginal cost, there your profits are actually maximized. So that should not be a surprise, because we're looking at a price-taking firm. So we did assume here that price is just given, it's constant. It's not affected by quantity, which would be the case for a monopolist. But for a price taker who takes this price P as given, it's not affected by its own production decision. Indeed, this gives price equals marginal cost, gives the maximum profits. So that's the end of this video, this lecture as well. There are some further slides actually in which I give some of the answers to the exercises that are posed in the slide. So try those first and then have a look at the answers to verify your answers. Also go ahead and try, of course, as many of the exercises from the book as you can, and have a look at the videos of the worked exercises, and go to the tutorial, of course, on Friday if you have any further questions. And I hope to see you then next time. Bye bye.